Hello everyone, my name is Sanskruti and today I'm going to present my poster on the 3D mapping of X-ray emitting ejecta in Kepler supernova remnant. Let's start with what's a supernova. Well, when a star dies, it explodes into a supernova, leaving behind gas and debris heated to millions of degrees. Kepler exploded in 1604 and this is how it looks today. We study it using NASA's Chandra X-ray telescope due to its unparalleled high resolution. Now we have 7 days worth of Chandra data. Now I want to emphasize that less than 10 PIs a year get this much observational data. Typically it's only a few hours, but we have 7 days worth of high resolution X-ray data along with 12 days of archival data, and we use this to create a 3D map of stellar debris which will help in theoretical modeling of stellar explosion. Now, in order to do that, we need to measure space velocities of regions. So, space velocities has two components, a radial and a transverse. Now, let's look at in a little bit of more detail how do we measure each of these components. Here, I show three regions, which is the very first step is selecting tiny regions across the remnant. N2 in north, T32 in center, and a southern region T18. We extract the X-ray spectrum of these regions and we see that in all of these three regions there are these silicon, sulfur and argon lines. What does this mean? Well, these elements are heavy elements and they can only be synthesized inside the star, meaning these three regions were all part of the star before it exploded and hence they are called the ejecta regions. Now we notice that the silicon is the brightest among all the lines. So we use this silicon line and compare it with the rest frame silicon line shown in green lines in figure 5 plots. So the Doppler shift between the rest frame silicon and the measured silicon gives us the radial velocity. A negative radial velocity means the region is moving towards us, which is in the case of T32. And a positive radial velocity means the region is moving away from us. Now the next step is finding the transverse component. So we track the motion of these regions across the plane of sky through imaging data. And we see that in year 2000, N2 was here in red, but in 2022 it has shifted upwards, represented in region blue. So the shift in this position gives us the transverse velocity. Now that we have both the components, we can find the space velocity and we see that N2 has a high space velocity of 8000 kilometer per second, whereas the other two has only 2800 kilometer per second velocity. Now we did this for about 30 regions and we created this map of stellar debris. And these we found that our ejecta debris have velocities of around 2000 to 8000 kilometers, whereas the CSM regions have very less velocity, less than 2000 kilometer per second. CSM regions are the regions which were not part of the star before the explosion and they were already surrounding the star. Now, here in the figure, you can see that the red and blue vectors are space velocities of red shifted and blue shifted regions, and yellow vectors represent regions with no significant Doppler shift. In future, we will expand our sample size to about 100 regions, and we will focus on revealing any deviation from spatial and velocity distributions of the spherically symmetric stellar explosion, which will provide astronomers observational constraints for modeling the true 3D nature of stellar explosion. That's it for me from today. For today, thank you so much.